In this example, we're asked to do some analysis here to determine the shear stress in a pin that's keeping this structure attached to the ground. The structure is made up of link AC. There's an applied force P which is acting there at the top. There's a cable which is attached at point B on AC. It extends down here to point D where it's attached to the ground. And so as we load it up with the applied force P, we'll put tension in cable BD, and then we'll be putting a shear force on this pin there at C. We know that the diameter of this pin is capital D, and we see that the joint here at the bottom, if we look at it from the edge, there are two surfaces that are going to be carrying the shear force. It's a two-sided pin. We need to keep that in mind in the end. In order to find the shear stress, we need to find the shear force. So let's do an FBD of link AC. We've got the applied force P. The cable force is going to run along line BD. The reaction force of CX and CY, like this. And we'll also have to deal with this angle of theta, where we see here from tangent theta is equal to 6D over 8D. So anytime we need tangent of theta, that's going to be the numerical value there of 3/4. First thing I'm going to do is write down a moment equation about B. Point B is where the cable is attached. The reaction force component CX has a moment arm of 6D. It's in the positive K. I guess I should define my X and Y. X like this, Y like that, so positive K is coming out. And then we have the applied force P, a moment arm of D, it's in the negative K. For equilibrium, that sum is a 0. So together we see that CX is equal to 1/6 of the applied force P. Summing forces in the X direction. I have minus FBD cosine of theta. The CX component of the reaction there at C, the applied force P, for equilibrium, that is a 0. So from that, we get that the FBD is going to be equal to P plus CX divided by cosine of theta. We saw that CX was equal to 1/6 P. Add that to 1, that gives us 7/6 P divided by cosine of theta. We sum forces in Y direction. We have FBD sine theta acting in the negative Y. We have CY, the Y component of the reaction there at C, equal to a 0. From this, we get that the Y component of the reaction at C is equal to the load FBD, which we just found, times sine of the angle. So that becomes 7/6 P times tangent of theta. The trig that we found above was that tan theta is equal to 3/4. So this becomes 7/8 P. So what we know at this point is the total reaction force that's supported by that pin there at C. So what I'm going to show is an in view of pin C. What we have acting on there is an X component of reaction, CX, a Y component. And what's important is not just CX or CY, it is the total resultant. C here is the shear force, the total shear force that's carried by that pin. And the magnitude of C is the square root of the sum CX squared plus CY squared. CX squared we said was going to be equal to P over 6. So that gets squared. Plus we just found that this y component was 7/8 p. That is squared. This becomes 0.891 times p. So this is the magnitude of the total shear force at C. Note that C, magnitude of C over 2 is the shear force carried by each face, where we have a double-sided connection. So since two sides carry the load, one surface carries only half of that. So therefore, the average shear force on one surface is going to be the magnitude of C divided by 2 divided by the cross-sectional area A, where A is pi d, the capital D, the diameter of the pin, divided by 2 squared. So this gives us that. So in order to know the shear stress, we had to find the total shear force first. We did regular equilibrium analysis, found the resultant shear force acting at C. We recognized that that shear force is split between two surfaces. It's a double-sided pin. We take that C, divide it by 2. That gives us the shear force acting on a surface. Take the shear force, divide it by A, and we get the average shear stress.